Hello, I am Solanti from the Customized Parallel Computing group at Tampere University. I am presenting POCL Remote, a distributed OpenCL runtime with a focus on low latency. GPU computing became mainstream a good while ago and brought great performance gains to easily parallelized problems, addressing the ever-increasing performance demands of modern algorithms and new problems. At the same time, application development has strongly shifted focus towards mobile devices as the main target platform. However, mobile devices are way behind desktop hardware when it comes to performance and additionally limited by their battery life. As such, many tasks are simply not feasible to run on a mobile device. The easy solution is to offload heavy workloads to a dedicated compute server, but as many applications require real-time results, network latency often limits the viability of such a solution. This is especially problematic on wireless connections that mobile devices rely on heavily. The latest generation of wireless communication standards, 5G and Wi-Fi 6, have reduction of first hop latency as an explicit goal, making offloading computations to a private cluster or cloud edge servers near the base station an interesting solution. In this context, POCL Remote was created as an OpenCL runtime that could make use of GPUs as well as custom accelerators over a network. POCL Remote is not the first such implementation, but prior solutions have been mainly concerned with throughput and seeing whether offloading OpenCL tasks is feasible at all. POCL Remote, on the other hand, has an explicit focus on minimal latency. Most networked applications rely on generic network protocols that have some kind of custom data format for the data being transferred over the wire. This adds a serialization and deserialization step on the ends of the communication channel, which has proven to have a significant performance impact. One of the methods used to achieve low latency in POCL Remote is the custom network protocol that unifies the in-memory and wire representations of OpenCL commands and data to eliminate serialization and deserialization steps. Most POCL Remote use cases assume the host application to run on a mobile device with modern wireless connectivity, that is to say 5G and Wi-Fi 6. Being radio-based connections, they are sensitive to other traffic and noise on the same and nearby frequencies, which contributes to packet loss. Practical latencies are still in the order of several milliseconds. In existing solutions, node-to-node data transfers generally go through the host application, which means they incur the limitations of the wireless connection twice. Remote nodes are assumed to be stationed in a private cloud or cloud edge cluster, meaning the remote nodes have wired, generally data center-grade connections to each other. This implies massively higher available bandwidth and lower latencies all the way to sub-microsecond numbers. For minimal latency to the mobile device, remote nodes are to be placed physically close to the wireless access point. In addition to nodes having great connectivity to each other, a single node can contain multiple compute accelerators. Communication between accelerators on the same node does not need to touch the network at all and thus has excellent latency and throughput characteristics in comparison. POCL Remote supports both node-to-node and accelerator-to-accelerator transfers and automatically chooses the fastest available transfer type. As mentioned in the previous section, POCL Remote aims to reduce total computation latency by eliminating data round trips through the host application. Not only are they wasteful, the remotes also tend to have massively better connections between them than to the host application. By supporting direct remote-to-remote communication, POCL Remote not only improves latency and power consumption on the host device, total network traffic is also reduced as the data only needs to be transferred across once, remote to remote, instead of twice, remote to host and host to the other remotes. One of the applications tested with POCL Remote is sorting of point cloud data for better rendering quality in an augmented reality application. On the left is the basic result with unsorted points. On the right is an improved rendering using alpha blending, which requires the points to be sorted by depth. The sorting is done on the remote and the results are written to an index buffer that is then transferred to the host application for rendering. Note the lack of rectangular artifacts on the right side. Another tested application is computer vision, namely computing TVL1 optical flow. This could enable scaling up to use higher resolution images or flipping the setup around multiple embedded devices in a setting such as a car to share a single accelerator for performing the computation. POCL Remote is implemented as a client library to be linked to the host application running on the mobile device. If the device has a native OpenCL implementation, this can be used together with remote accelerators. Planned improvements for the future include on-the-fly detection of available remotes and roaming between remotes as network conditions change. To further reduce latency between nodes, remote direct memory access seems worth investigating. We are also looking to extend support to Vulkan compute shaders for uses such as distributed path tracing in virtual reality applications, and are interested in hearing about more benchmarks and application scenarios. Thank you.